The next transfer function that we will consider, or so-called building block that we will consider, is a transfer function that has a 0 at the origin. If you recall what a 0 is of a transfer function, well, that is just the roots of your numerator, or if you want to again think of this in an alternative way, it is the value of s that causes your transfer function to go to 0. And in this case, of course, if you plug in a value of 0, that means your transfer function goes to 0. Okay. We can easily plot the Bode plots of this transfer function using the tools we developed previously for plotting the value of the Bode plots of a constant and the Bode plots of 1 over s, because we can rewrite this transfer function as 1 over 1 over s. Okay. Now the key to making this easy is to realize that if we are plotting in the log domain, then, well, a division just becomes subtraction in the log domain. So in effect, what this means is that we can plot the response of 1 and subtract, we can subtract the response of 1 over s from the response of 1. Okay. So to show you how you do this, let's plot the Bode plots of this. Okay, this is decibel again. That's the angle. Okay. So what we're going to do is we're going to plot the magnitude plot of 1. Well, the magnitude plot of 1 is 0, because if we take 20 log of 1, that's just equal to 0 dB. Okay, so let's use colors again. Okay, so that is 0 dB. And the phase of this constant is, of course, just 0 as well. How does the magnitude plot of 1 over s look like? Well, if you recall, we know it goes through the 0 dB line at 10 to the 0. And it has a gradient of negative 20 dB per decade. And the phase of 1 over s was, of course, negative 90 degrees. Over 0 degrees. Okay. So to get the Bode plot for the overall transfer function, or the T of 4 of s is equal to s, well, we can just subtract the magnitude of this 1 minus the magnitude of this 1 over s. So if we take specific frequencies again, let's take this frequency. Well, the value corresponding to the constant 1 is 0 there, and the value corresponding to here, let's call that just v. Well, that's 0 minus the value of v, so that just becomes negative v. Okay. Here, both of them are 0, so it stays at 0. And let's take this frequency again. So the value corresponding to the 0, the constant 1 is 0 dB, and the value corresponding to the 1 over s is negative v. So that's just a v. So we're going to take 0 minus v. Well, that's just positive v then. So it becomes, goes at the top there. Oops. Okay, so if we connect those lines, we see that it in effect just becomes the reflection, the magnitude plot of S just becomes the reflection of the magnitude plot of 1 over S. Okay. So for the phase again, we take the phase of the constant 1, which is 0, and the phase of the 1 over S, which is negative 90, and subtract them from one another. So for all frequencies, both of them are constant, so we can just see that if we want to get the phase of the transfer function S, we take 0 minus 90, so that just becomes a positive 90. Okay, so whenever you see a transfer function that has a pole, a 0 in it, and it will of course be in the numerator, then you know that, well, the magnitude plot for that S is just, it crosses the 0 dB line at 10 to the power 0, and it has a gradient of 20 decibels per decade. And the phase of a 0 is a positive 90 degrees.